Okay, so n is the number of nuclei. Literally, this is a number as in if I had 12 grams of carbon, I would have roughly a mole. I'd have like 6.02 times 10 to the 23rd atoms. So we're talking about a huge number here. This is a huge number, and it's not a very practical thing, but there it is. Okay, and then lambda is was wavelength, right? And even though there are, again, there are 52 different letters we could use, and then there's the whole Greek alphabet, so that's 104. We use the same like 8 over and over and over. Okay, so lambda in this case is not the wavelength as it recently was, right? This is actually the per second probability, decay probability. Right? So if every second there's a 50% chance that you're going to go boom, the Heisenberg uncertainty principle will roll the dice, and it's a 1 instead of a 0 or something like that, right? And it's a two-sided dice. I guess that's a coin, isn't it? Okay, flips a coin, right? 50% chance you decay. Then this would literally be 0.5. It's just a decay. It's a pure number. Okay. There's a 1 in 4 chance. If you got a 4-sided dice and you roll it, and if it's a 1, you decay, right? Then it's 0.25. Literally, that's what it is per atom. And generally, these are vanishingly small because there's a lot of atoms, and every one of these little decay events is, every single one of those things is one of these events happening. That one of those atoms, one of those 6.02 times 10 to the 23rd atoms, or very large number, has rolled the dice, and it rolled whatever number it is that made it decay. And there's no hidden variable model that makes it any better than that. It's just probability. Okay. Now, these rocks are going to be radioactive. They're probably uranium things with like billion-year or hundreds of thousands of years of half-life, right? So they can decay for billions of years and still have half of them left, right? And the reason why so many are happening per second is that there's a lot of them. Yeah? Yeah? Kind of a thing, right? There we have it. No, yeah. No uranium leaking. Okay? And then A is activity. It is the decays per second. And I'm looking for this in your data packet, and they have this formula in there. Okay? Now, this is very simple. Okay? The formula is that activity is equal to the per second probability times the number of molecules. So if there are 20 of you, let's imagine that there are 20 of you. Yes? Are you picturing this? And you have a 1 in 4 chance of decaying. On the average, if we did it enough times, how many of you would decay in the first second? That would be 5. It would be a quarter of you. Yes? A 1 in 4 chance, 5 of you would decay. Does this make sense? And if there were 200 of you, there were 50 would decay. Yes? Okay. Now, if there were 200 of you, it'd be much closer to 50 than if there were 20 of you than to 5. You know what I'm saying? Because 20 is not a very big sample. How about if there was 2 moles of you? Well, once you get down to 2 moles, that's so many trials, so many dice flippings, right, that this number just becomes exact. Exactly a quarter of you will decay in that first second. Exactly. Now, again, there might be like 1 or 2 atoms more, or, 100 more, but that's so small, right? So when you start sampling enormous things like moles of stuff, right, this just becomes more and more exact because of the way sampling works, right? Okay. So this is our first example, I believe, right? Radon-222 has an atomic mass of 222.02. How many grams of it do you have if your activity is 8.249 times 10 to the 16th decays per second, and your decay probability is 2.098 times 10 to the minus 6th probability per second? This is vanishingly small, yes? This is like, 2 parts in a million, yes? Okay? So that's a very small probability. And then what do we need to know? There are 4 clues here. The first one is Avogadro's number, right? And that is that if we had a mole, that it would be 6.02 times 10 to the 23rd atoms per mole. The second clue is that the number of moles we have is the number that we have divided by Avogadro's number. So if we have 3.01 times 10 to the 23rd atoms, then we got half a mole, right? N is 0.5. And then N is also equal to the grams you have divided by the molar mass. Isn't that the molar mass? Yeah? That's its molar mass. Okay? So it is the grams you have divided by the molar mass. In fact, we had even more sig figs than this, but we don't really need more than 5. Right? I mean, honest to God, we could just keep going, because if we had radon 222, we're not talking about like periodic table accuracy. We're talking about we can look it up from the mass spec data in Appendix F or whatever that is, right? Okay, what's the fourth clue? What could be the fourth clue? Oh, that formula. There we go, right? Okay, so I think what we can do with this example is that the first thing to do is to figure out the number of atoms we have, right? So if the activity is lambda n, then our activity is 8.249 times 10 to the 16th. And this is decays per second. But decays is not really a unit, so it's just per second. When you say it, you've got to pretend to say something. You've got to go per second, right? Right? And if it's something like radians, which is like meters per meter, then it's like, doesn't have any units. It's like, right? Okay. So this equals, and then we know lambda. So lambda is there, 2.098. Right? And this is times 10 to the minus 6, and this is just, again, per second. Probability per second, but probability, again, is a pure number. Whoops. And of course, what are we going to get? Decays per second. Then we're looking for n, yeah? I think we just divide. Don't we just divide? I think we divide. So let's just try that. Okay, so it's going to be 8.249 e to the 16 divided by 2.098 e to the minus 6. That's a lot of atoms. One atom, 12. Okay, so this is, n is equal to 3.9318 times 10 to the 22nd atoms. Don't we want to figure out moles next? Because I think if we have moles, we can find grams, right? And we want to know grams. So if I divide this by Avocado's number, right, so let's divide this by 6.02. We'll see how many moles we have. This is atoms per mole. You could spell mole with an E if you prefer. It has a more vivid mental image. Do you guys read Redwall books when you were kids? Yeah. Thank you, madam. Oh no. Oh no. Brian Jakes died. This is so sad. We read those books until the kids just sort of outgrew them, and we never read them all. There's so many in there, you know. And it's not like, anyway, they were good. This is moles, right? So now we've got how many moles we have. How do we go from moles to grams? Times by the molar mass, right? So the final thing here is that we're going to go 0.065313 moles times 222.02, and this is grams per mole. Aren't you curious what it's going to be? 14 and a half. Look at that. I think I worked this one backwards and just made the answer 14 and a half. Because 14 and a half, that's a good old number. I know, yeah. Your average number that, there we have. It's actually 14.501. How many sig figs do we have? 5. We have 5. We had 4. 3. So yeah, even with 4 sig figs, there we go. Huh? You've got n equals lambda n on there. Yeah? Is that okay?
No, I mean on the PowerPoint.
Oh, n equals lambda n. That's kind of funny. Yeah. Don't pay any attention to that. What's funny is that I'll save this, right? And this is not the master copy.